but I just clicked to record on Cloud. It's very easy to forget. So it's now recorded. Oh, so by the way, is it okay to record this session for people to watch later?
Sure.
Yeah, thanks. Yes.
Okay, so since it's now recorded, let's start. Okay. All right, so welcome everybody. So my name is Zihan Zhou, and I'm an assistant professor in the College of Information Sciences and Technology at Penn State. So I'm a co-organizer of this workshop, and I will also be a co-host for this panel together with Professor Yasutaka Furukawa from Simon Fraser University. Good morning, Yasu.
Good morning. Maybe just to introduce myself, I'm Yasu Furukawa from Simon Fraser University. I'm not the panelist, maybe ask some questions. So I'll try to be quiet as much as possible for others to speak out.
Okay, so next, it's my absolute honor to introduce a group of people, our panelists, who have really laid the foundation and done tremendous work in holistic 3D vision. So I will probably start in this panel by inviting everybody on the panel to give a very brief, like 2 to 3 sentence self-introduction. So let's start with the alphabet order here. So the first person will be Amir. Hi, Amir.
Hi. Well, I'm Amir Zamir. I'm an assistant professor at EPFL. Well, I'm glad to be here. I'm not sure, is that the level of self-introduction we're looking for here?
Very good, thank you. Good morning, Amir.
Yeah.
The next one is Daniel.
Hello, yeah, thank you. I'm Daniel Aliaga from Purdue University. I work in things related to urban modeling and computer vision. So try to take advantage of the particular structures of urban environments to help with their reconstruction, as well as modeling their function for things like city planning and urban design. And thank you very much for inviting me to this wonderful workshop.
Thank you. Good morning, Daniel. Next one, Florent.
Hello, everybody. Thanks for the invitation. I'm Florent Lafarge from INRIA and Sophia Antipolis in the south of France. And I work in the Titan team, and my research topic is focused on city modeling and surface reconstruction and approximation.
Thank you. Good afternoon.
Good afternoon.
The fourth panelist, Manolis.
Hi, everyone. My name is Manolis Savva. I'm an assistant professor at Simon Fraser University. I've worked on procedural modeling of 3D scenes, more recently on 3D simulation using 3D scenes. And I'm very excited to be in this workshop. Yeah. Looking forward to the conversations.
Thank you very much. Good morning. Actually, we have Marc here. I just promote him to the panelist. Hi, Marc.
Hello.
You joined at the right time.
I was watching already, so it's all good. Marc Pollefeys, I'm a professor at ETH Zurich, and also the director of the Mixed Reality and AI Lab from Microsoft here in Zurich. I've been excited to work on all types of 3D kind of geometric computer vision problems for, like at least the last 20 years or so, 25 years. So very excited to be here.
Thank you. Okay, so let's move on to our next panelist. That's Niloy.
Hello. Hi, everyone. Thank you for the invitation to this panel. I'm Niloy Mitra from University College London and also Adobe Research. My interest is in geometry processing, both analysis of objects and scenes, and also for generative tasks, both for object appearance as well as geometry. Look forward to the discussion.
Thank you. The seventh panelist is Shubham.
Yeah, hi everyone. I'm Shubham. Very excited to be here. I work at Facebook AI Research in Pittsburgh and have worked a bit on learning-based 3D reconstruction, primarily focusing on single view reconstruction.
Thank you. Professor Ima.
Hi everyone, this is Ima. Again, also I have been also working on 3D vision, multi-view geometry for 20-some years. And also I also worked on some of the learning methods for high dimensional data. Yeah, thank you very much for inviting me. Thanks.
Okay, so I guess we have everybody introduce themselves, and it's really our pleasure to have everyone here. We have a really great group of people for this discussion. So let's start with our first question. Okay, so this question is kind of quite general, and I guess from many of your talks, you mentioned the repetitions for 3D models, which is a very important design decision to make for many 3D vision problems. So given that we have so many choices from meshes, polygon soup, volume, smooth surfaces, boundary, primitives, path-based, and scene graph, how do you know, like from a practice point of view, how do you know which one is better than the others? Can you somehow give us some idea how we can quantify and compare the different representations? So we can start maybe with the same order for this question. So I guess everybody might have something to say. So let's start with Amir.
Sure. I think generally, to me, the choice of representation that you choose for either semantics or 3D data, I don't think 3D data in this case is different from semantics in terms of the choice. It depends on the downstream task. Like, what do you want to do with your 3D representation? So I think that's generally has been true for most of the things that we do. So in my case, I'm interested in turning these 3D understanding that we extract from visual data for robotics applications. Basically, an active agent is provided with some general goal that to do in an environment. The question is that what kind of 3D representation we want to use to be the best enabler of the downstream action. So I don't think commitment to any representation make total sense here. As just like in humans, what is the 3D representation on our head? It's probably not going to be a single thing. It's going to be a fluid like interaction between different representations and transition between them. So the short answer is it depends what you want to do on the downstream task. And the things that I'm interested in, I think what's important is to enable a fluid transition between different representations. I think the 3D scene graph is something that I discussed. It's something that enables you to integrate semantics and 3D in one unified representations, but that's something that is rigid on its own, I have to admit. So ideally want to move towards representations that are like more fluid in terms of allowing themselves to restructure and so on. And all those things would have to be determined based on a downstream purpose. So that's my answer.
Thank you. So Daniel?
So I would agree that it depends, but maybe one aspect also to think about with regard to downstream usage would be, while there are many representations, you might also want to organize it in some way, call it hierarchy or grouping and things like that. And that might have more of an importance in a way in which you do that than whether you choose as the atomic unit to be points, triangles, or patches. Is how you organize it. And such hierarchical organization, for instance, might be very useful, particularly if you wanted to put some semantics on. So I'd worry more about the organization, hierarchy or grouping than I would about whether you use points, triangles, or patches, for instance. Next.
Florent?
Yeah, so I agree that it really depends on the need of the end users. Now there is one type of representation I quite like because they're pretty generic, is the ones that are based on combinatorial maps, because they can represent volumes, they can represent surface, they can represent linear structure. So they're quite generic and they can actually tackle a lot of problems. And they are particularly well adapted for piecewise planar geometry. If you want to, you assume you can describe any object based on the assembling of planes, of collection of planes. So this type of representation are quite generic. If you assume that yeah, your object can be described with, I would say, basic surface and volume primitives. But now really it depends of the need of the end user. If you want to do a basic rendering, basically point-based representation is probably enough with the existing algorithm today. So you won't need to have more, for instance.
Thank you. Manolis?
I think I pretty much agree with what's been said so far. It really depends on what downstream application, what task one is interested in. With a couple of caveats though, a couple of thoughts from my end. One is there's an advantage to being as close to your input as possible, right? If you're considering these kind of sensing aspects, you know, data coming from the real world, then, you know, usually that's kind of, you know, it's sensing surfaces. We're talking about, you know, range sensing, LiDAR sensors, depth sensors, and so forth. So you usually get point samples from the surface. So it makes a lot of sense to start from that representation. You're not introducing any, you know, conversion to a different representation. You're working directly with raw data that's coming from a sensor. So in that case, I think it makes a lot of sense to focus on that. The other caveat, the other thought is that it makes a lot of sense to exchange between representations and choose one where the operations that you care about are easier or are more obvious. You know, for example, if you care about, you know, physical simulation, many times you want to have, you know, manifold surface representations, right? Or, you know, you want to have some representation of the volume itself. So you want to have a volume representation. So when particular kinds of operations are important to you, then you should choose the representation accordingly. So those are just my two thoughts on top of the general statement that it depends and we should be flexible in terms of our choice of representation.
Yes, I guess everybody wants to hear some more guidance than just it depends. All right, so Marc?
Okay, so well, I agree with pretty much everything that's been said. I think that besides, you know, on the one hand, the dependency on the output, the dependency on the input that we've heard, I think also very much that the representation is often critically linked, at least the intermediate representations, to the algorithms themselves that we would be using. And so depending on what we're doing, that's a little bit like what Manolis was saying in terms of the operations we care about, like intrinsically what the algorithm is doing. We might really want to use different algorithms. So there's really often quite naturally you might go from the input representations to then some that you would, you know, your algorithms might be well suited to kind of manipulate and do operations on to eventually then convert or bring it to something that that the end user will need. You know, I think like as you want something more concrete, you know, like in recent years, really like some of these implicit representations that have come up, and so that's, for example, quite nice as, you know, as a complement to some of the explicit kind of triangle and mesh-based representations. But you know, again, it does depend on what you're actually trying to do.
Thank you, Marc. Niloy?
I think this is a great first question for any panel, because there is no right answer. No one will ever give an answer. You ask this in 10 years, it'll be the same situation. I think what we have seen in the recent years is the ability inside the algorithm to be more flexible and operate across different representation. For example, the input might be in a volumetric form. The underlying representation or optimization might be maybe at a mesh level, and the final loss function at the image level. So instead of looking for the best representation, we might think more about how we can very effortlessly go from one domain to another. As has been said, certain operations are just easier in one representation than others. And I can see this across the works, across many recent works, and particularly many on this panel. I think many of us have been using this and exploiting this. Something that I have found in my years of working on this one that works very well is explicitly having an explicit handle on the connectivity or the topology of the objects. And that in our group, what we do is we keep a very simplistic geometric representation of boxes, as simple as that. And then having explicit connectivity handles between the parts, something Manolis has also used many times in his work and others. So that would be my input to this problem, to this question. Thanks.
Shubham?
Yeah, so I basically just want to expand on the "it depends" answer by saying that there's one additional aspect also, which is, the ease of predictability that comes into play. As in, we were thinking of what operations it enables in terms of what users we want, but how given the tools that we have, like deep learning networks, etc., some representations are inherently more amenable to being inferred via those. And for me, that is something that comes into play a lot. For example, if you're thinking of meshes, then being able to infer meshes, let's say from images that can accurately handle arbitrary topologies, much more difficult than, let's say, volumetric, implicit or explicit representations. So yeah, again, maybe the answer is it depends, but I'd also say the predictability or the ease of connecting these to certain tools that we have is also a big factor that we need to consider.
Yeah, I think that's yeah, I particularly like the way about the different metrics or criteria we may use to compare different representations. For example, as you mentioned, like how easy to use and how efficient, maybe how robust, and maybe how compact. Yes. The question is, probably the next question will be, can we somehow compare those different metrics in a more unified way? Because now those things are really hard to quantify from my perspective.
Okay.
Now we have Professor Ima.
So this is, I think, I like to answer a question just from a story, my very personal story, right? So when I was a graduate student, I work on structure for motion, meaning for the first project is for the car, and second is for the helicopter landing for Navy at the time, try to have an autonomous helicopter landing on the pad. So from so at the time, at the lower level, if we want to just track features and estimate the position and orientation of the helicopter, point cloud tracking features, triangulate bundle adjustment, actually solve the job. But later actually realized that, so you have to design a landing pad because the pilots recognize where to land. Right, that's a human function. So having the landing pad distinguish itself from the rest of the world, right, the objects from the rest of the world. So that actually made us a little realize that we have to design something that so the helicopter know where to land. And then realize that it's a flat surface and also with some shape, right, H whatever pattern on it. So later on, we realized, okay, fine, we can help the helicopter distinguish where to land now. But then later on, we realized that we can actually use the path is symmetric. So maybe we can use it for orientation. Honestly, that's the first question in my life. Led me to study what is a symmetry. Something with a pattern will actually help. Well, sometimes hurt, just like in Marc's situation, right? So you have a symmetry, you can have ambiguities as well. You have to resolve the ambiguity, but sometimes it also helps to get a much more accurate position. So that's actually a very personal realization, right? So as a simple example, and also carried to this day, because there are many problems we need to solve with local features, point clouds, and also mesh, and so on. But gradually nowadays, I think 3D vision has reached to a point we try to offer human user something. Even for that reason alone, right? For AR, VR, mixed reality, it's very hard to present a user, average person, with a point clouds, with a mesh, with a voxel, a very low level representations, I would say, right? So you have to present something very highly semantic associated with object level. It's just like recognition, people start from pixels to now to semantic. I think geometry also has the same kind of mission. If we want to have this to really leads to a good interface to interact with humans, we have to present people something much easier for them to comprehend, some kind of abstraction, right? Resonant with some of the panelists as mentioned about the hierarchical representation. But we have to make this process very, very robust and very, very, very easy to use. Even for that purpose alone, we have to make 3D vision in a way very friendly to this kind of human interpretation. So that's, I think, also one of the reasons we had organized a panel like this or the workshop like this in general.
Thanks, E. So I'm going to pass the opportunity to ask the next question to my co-host, Yasu.
Yes, thank you, Zihan. I'd like to thank again all the participants for joining. I usually like controversial question. In the first question, people come tend to agree. So I try to be controversial. So this is about end-to-end learning. So there are, I guess, many bubbles in computer vision. When I started, there's an eigen bubble. If you formulate your problem, an eigen problem, you get a paper. Maybe it's the sins of the normalized cuts. Then maybe I forgot the order, but maybe sparsity bubble. L1 normal optimization, you get a paper out. Then convexity. If you can approximate a sequence of convex optimization, yes, you get a paper. You have a deep learning bubble. Then we have an end-to-end bubble. You put everything together end-to-end, you get 2% or improvement in performance, you get a paper out. I'm kind of not excited with this end-to-end myself. There are some exciting end-to-end. It's important to make something differentiable. It can do many things, but usually often not excited. So I wonder, which side are you? Say somehow God of computer vision tells you either have to use only end-to-end. All the data go to GPU, done. That's the only thing you can. Or you have to be hybrid. GPU, you have to get back data to CPU, then back to GPU. You have to do hybrid or end-to-end. Which one do you take? My answer is hybrid. If I pick one instead of end-to-end, so I don't believe in end-to-end much. So I wonder which one do you pick? And for this question, maybe instead of asking everyone to speak one after the other, ask you to raise your hand physically here. I can see. So if anybody has, maybe some of you, which one do you stay? Hybrid or end-to-end? Yes, Marc?
Maybe I want a clarification first. When you say end-to-end, do you mean like it has to be like a black box with just a network inside? Or can it be, a hybrid thing with just, propagation end-to-end, back propagation end-to-end?
Yes, but back propagation, maybe differentiable. So anything have to implement differentiable and train back to back. Yes, so then, so Marc, do you have, oh yes, maybe Amir?
Oh, Marc, did you want to go first?
No, then I think it's not so controversial. Then, like I think I could just go with differential if, like it doesn't take too much trade-offs along the way, but.
No, I think it's, well, let me first say one thing. I think there's one point here to demystify. I think end-to-end does not mean necessarily giving up all the geometric knowledge and so on that we know, right? You can integrate them within an end-to-end framework. If you know how to do it. I think the criteria right now is being differentiable, but like, let's say at some point, if you have something other than deep learning methods, the criteria might change. But let's say if you know how to solve one problem like geometrically, there's no point in throwing a neural network at it to simulate the geometric process that you have, right? So we can think of that as using the geometric process as some sort of inductive bias within a neural network, and that's what we frequently do. Like we frequently, you know, if you say put a raycasting, like differentiable raycasting layer within your neural network, is that end-to-end? Yes, this is still end-to-end, but then it's not like you have replaced a geometric process that you already know how to solve mathematically with neural networks. So in my opinion, the answer is obviously it has to be, or just beneficial to go hybrid, because if you know how to solve one problem and you know exactly how that should be, and you know the answer geometrically and mathematically, why would you want to let a neural network to reproduce that with a lot of data? Because math and theory works. But then there's this beauty there that, especially let's say in biological organisms, if you get inspirations from them, is that somehow data goes in and beautiful behavior comes out of it. And not everything in this process, at least existing theoretical knowledge, tells us how to do it mathematically and so on. So that's when something like a connectionist method like a neural network is useful, because it kind of like you have block, and we have some of these blocks recovered theoretically and through mathematics, and some of them are unknown. So these neural networks, I view them as a glue between these different blocks that let us through this, like flow the signal from beginning and end and get something that is, doesn't require like engineering like between these different blocks, but it's still end-to-end. It still respects sort of the mathematical knowledge that we have developed. And so I don't really see the divide to be between going end-to-end versus giving up the things that we already know theoretically. It's more like how to actually use this. Like there are different ways that you can use it. Like in our work, when we use something like let's say depth estimation or normal estimation and so on within an end-to-end framework, that's basically like making use of some of the stuff that we already know, but turning it into some sort of inductive bias, and you can turn your mathematical knowledge into inductive biases. So, well, in that sense, I would say I would be really curious to hear who would say, let's go end-to-end and forget about those like mathematical knowledge that we have. Like, why would you want to do that?
Thank you, Amir. Maybe I see Niloy's hand. So Niloy, then Daniel next.
I think Amir covered most of it. I do want to say, for certain applications, not that the type of work I'm involved in, end-to-end might be justified, even if it remains a black box, if the end goal is just performance. Right? But there is, so I think that's an absolute practical win. Right? But there's something we are saying, it's either hybrid or end-to-end. But in an ideal world, we would, if the end-to-end is doing better, in an end-to-end version, which is not motivated even by the geometric model, let's say it's really a black box end-to-end, it can be one of the two reasons. One is it's overfitting to the data when it's not very useful. The other is it learned a better model. And even for something as simple as a camera projection model, we know it's at best an approximation. Yeah, so we are not considering, say, refraction. We are not considering the lens effects, etc. So the best answer, or the best thing we can hope for is even if we use the end-to-end, we can then read out what is the corrected model, or what is the model plus the correction, which is maybe first order or second order effects, and then use it as our model from then on, whether for camera or for other modules.
Thank you. Now maybe to Daniel. Then after that to maybe Shubham.
So I guess I hear this more about, or think of this more in terms of, are you gearing for supervised or mostly unsupervised or for supervised learning. So if you have a complicated problem and you just want to make one big unsupervised network, a set of networks, that's definitely more challenging, less likely to just magically work. So if you break it down into pieces, then, and you have a hybrid approach, that's more likely for these larger, more difficult problems to kind of do something reasonable. Maybe then you can do a refinement end to end at the end, right? So I think it's more about the other parts of the problem. So if you're doing a supervised problem, that's kind of less challenging nowadays, perhaps given some of the abilities. So therefore, sure, you can be unsupervised, you kind of understand the aspects of it. But if you're solving a more challenging problem and you just make a huge end-to-end system, it probably won't do anything useful. So maybe it's about a level of understanding. Once you know the structure, the right loss functions and so forth, then maybe you can be end-to-end. Otherwise, you should not be. And that could be hybrid or not. That's my thoughts.
Straight, yes. We also have both voices, end-to-end hybrid. Shubham, or did you raise your hand? Yes.
Yeah. So I think there's one notion of end-to-end, which, as Marc said, if you're allowed to incorporate inductive biases, then I think all of us would say that that's sort of good. But one alternate interpretation is if end-to-end, if you say, requires me to only use backpropagation and gradient descent to solve all optimization problems. That is, if you were to tell me that gradient descent is the only optimization tool you're ever allowed to use in your life, and will that solve all problems of interest? Towards that, I would think maybe no, in that there are a lot of problems where thinking of discrete possible solutions or mixed integer programming is fundamentally important. And we do a lot of song and dance to incorporate some of those things in our end-to-end frameworks. And I'm not sure that is ideal, or if the current optimization tools we have will necessarily be sufficient. Like nature does have some discrete optimization through evolution. And I would hope, or at least my personal feeling is, just gradient descent won't necessarily solve all problems of interest. So maybe that's just one counterpoint against end-to-end as it's currently used.
Thank you. Maybe one last, either E, you're raising, yes, maybe we get voice from E, and then we'll go to the next question. So E, you're still muted.
Yeah, so I just want to make an analogy, right? So are we happy with the black box practice? Yes, I mean, history, we have plenty of wonderful black box practice, which is we call arts, right? Artists, craftsmen, we train, apprentice. We don't have to explain things. Apprentice just follow or learn things in a sort of empirical way. Wonderful, beautiful arts come out. Michelangelo, right, came out of this process. And that's actually great, right? From a practical point of view, can even generate masterpiece, achieve. So this is one way of practicing things. Another way is practicing is we call it more like science, right? We have also Einstein. Would we be happy to have a gigantic computer if we, back 50 years ago, can predict the motion of celestial or the stars? Fine, we'll be happy. Maybe some physicists will be happy about that, right? Give you precise location, what's the next star going to be at, right? Even potential at atom or simulate quantum. Would be happy with that. Maybe some people will be happy, or maybe also useful for, simulate nuclear bombs. But I think it's our human nature. We want to know there are other simplifying laws, right? Abstraction from that, right? I will be, we still marvel at, Einstein's formula or Newton's formula, which capture the complexity of the world with a very simple law. I think that's the same thing with our neural networks, our brain, how they function. They must be governed by some very simple laws, despite the complexity. Now, back to the question of black box. We should ask ourselves is that, Is there any scientific evidence that our brain is using backpropagation or doing gradient descent, especially through all the layers? I don't know. Personally, I haven't read anything in that is substantial or conclusive or even suggestive at this point, right? So that's actually a very interesting question for us. If we put our belief in something, if we want to be long-term, we should probably going after the evidences. Of course, again, by the way, right, if we have a powerful resource model, we can fit data, and also that actually solve some of the practical problems. Go with that, right? So that's nothing wrong with that. But as scientists, as researchers, I think there are much deeper questions we have to ask ourselves so that we can progress, right? So that's my slightly higher level answers to the question.
Yeah, thank you, E, for interesting insight. Maybe Marc, you want to say?
So maybe I wanted to kind of ask a question like related to the panel. My understanding with really black box end-to-end with the current deep learning methods, you know, you have the input space, the size of the input space, the size of the output space, and then there's some kind of, you know, either implicit or explicit latent space in the middle somewhere. I have personally, or I've not yet understood that we can go beyond explicitly sampling the full exhaustive implicit space to get any success with end-to-end deep learning. Can anyone tell me that's not the case, that there are methods that actually really have demonstrably gone beyond this? If not, it means that any kind of larger space will not be tackled with current methods because it will just randomly predict things when you go outside of the space you've actually sampled. A little bit too far from places that you've actually fed it information.
Exactly.
So I'd love to hear if somebody can tell me wrong here.
Anybody has the answer? That's Shubham.
Daniel has a
maybe
comment.
Daniel has.
So I would have a comment that while I agree if you don't sample the space, it won't converge, but synthetic stuff, synthetic generation is powerful. So you might be able to supplant the lack of information, say, of real data by appropriately generating synthetic data. So your question would be, yes, you need the samples, but they need not be real if your synthetic version is sufficiently good to replace it.
Yes, but I strongly agree. If you have to sample a 10-dimensional space, and that's not high, for the complexity of the world, that can be super expensive. I mean, this can be well beyond what a computer can generate over infinite time.
Could be. But you guys have big computers over there in ETH.
Yes. So maybe Shubham, we get yours, then move to the next question.
So not exactly a counterexample to what Marc said, but just a way of encouraging generalization. So for example, if we look at a lot of multi-view reconstruction approaches, if the way they sort of perform aggregation is there's a fully latent variable that represents the entire image, then they will generalize much more poorly because you need to have seen the entire image or densely, or sort of seen all kinds of images for that function to generalize. But if you have inductive biases that do more patch level or voxel level aggregation, then we have seen evidence that those systems generalize more strongly because now you're generalizing at the level of patches as opposed to entire images. And maybe that's just something to keep in mind when we are thinking about generalization. But yeah, again, it's not a counterpoint to what Marc said, it's just a way to encourage more generalization in certain cases.
So if the space is small, it works.
Yeah. And there are ways we can make it sort of smaller.
Yeah, no, I agree. You can do a lot of things. I certainly don't disagree with that. But
yes. Although maybe Niloy may want to say something, but let's move to the next. Oh, yes.
I just want to say, I think it reiterates what Marc was saying, because when this is coming from the geometric observation that the space of all possible shapes is much higher or much bigger than the space of all possible patches. And hence it's much easier to learn on the space of patches because there's just fewer variations of this. So that's what it's happening here.
Thank you. Yes, I guess we got to hear interesting discussion. I hope it was a bit controversial for people to share insights. So maybe Zihan, I'll switch over, hand it over to you for the next question. You're still muted?
Hi.
Yes.
Yeah, so sorry, I just got some internet issue. So I guess it just got the question on the end-to-end versus hybrid.
Yes.
All right. So my next question will be similar in terms of like you have to make choice, or I don't know. So nowadays, as we know, like the implicit representations has become more and more popular partly because of the surge of deep learning. And in the meantime, like the CAD models or the models of, you know, parts are more explicit. So the question is, what do you think in the future? Are we going to go with implicit representations more, and or we want to go hybrid, or when we want to go CAD models more? Which one do you think it will be for you in the future? And let's see.
I see Niloy's hand.
I want to say something here, because I will also have to leave at the end of this hour. I think I'll slightly change the question to answer something that is I'm interested in, which is we had the discussion about the representation, and we talked about representing the geometry in different forms. But in theme of today's workshop topic, I would like to discuss more about the holistic angle, where we are talking about the geometry and the appearance, and also maybe how it's going to be used, or the functionality of the object. And in the same representation, this hybrid representation that models both the geometry, whether in one of the forms we discussed, and appearance as an explicit color information, material information, or even a deep feature that is learned along with the corresponding rendering function or corresponding simulation function. I think that's an aspect that I expect to see much more being utilized, because that part we haven't explored and exploited sufficiently yet. So that's a form of representation I expect to see a lot more happening in the next years.
Again, I will just say from the way we use, right? So don't forget, I mean, the level sets implicit representation was very, very popular for this origin was really about scientific computing, has the advantage of really be able to capture the details, topological changes, and so on, and expressiveness. However, so that's has its purpose, and also, but there's a cost associated with it. Even at the time when you're done with computing, how you're able to access the information being computed. Now, but from computer vision, many of our applications, 3D vision, we are offering to average people. Now, just ask yourself, right? When you interact with people, you go to a shopping mall or unfamiliar places, ask to get to a specific designation. What kind of information you like to communicate, or people communicate between each other to convey the notion of 3D space and shapes, right? Would be implicit or explicit, right? I think in terms of computing to get the knowledge or recording 3D shapes or stuff, maybe the implicit will be very, very useful. But when really come to the system offers something for 3D vision for people to use, I think the representation has to be dramatically different. Yeah, more explicit and abstract, high level.
Florent?
Yeah. So from my point of view, today, maybe in a few years, I will have a different point of view. But if you want to have a chance to represent complex CAD 3D models that approximate, for instance, what a designer can do or something like that, I don't see how today we can do without using explicitly a representation. If I look, for instance, just if you want to extract some polygons in images, a polygon is a kind of, I would say, that simple CAD 2D model in images. And if you look at a deep learning method that has been designed, they still don't reach the result of, I would say, the standard method. And now there's a lot of question on how to add a vertex, how to remove a vertex, how to change the dimension of the polygon, how to modify the polygon to adapt to the shape. And there's no evidence today that for 2D that it will in the coming years outclass I would say the traditional method of vectorization or something like that. So if we go to 3D, assuming that, I would say it might be possible, but I don't see a solution or way to do that in the near future.
Thanks, Florent. Actually, I have a follow-up question for Daniel, because he might be leaving soon. Yeah, he was already left.
Yeah, I think he left. He told me that's a message. He has an appointment.
Okay. So never mind. So Yasu, do you want to pick up the next question?
Yes, maybe along the same line again. This one is hopefully controversial again. So in short, does Robocop or Knight Rider? Sorry, classical. My generation is a bit older. They don't need holistic representation, maybe. So robotics are coming. They also research on implicit representation. For navigation, don't build a map explicitly. So some special neural latent representation of a map. Go to this location, car can go, without having explicit map. They are interesting research. So as we see more and more autonomous agents, maybe we should worry about holistic research is going down. The robots don't need. Or you might say you can represent latent space. Then you can actually decode it to explicit. Maybe that's hybrid. Always hybrid is better when you have two systems. But if you do that, why not just hold explicitly? Why do you bother having implicit and decode? So which one do you like to prefer? Having all implicit, because Robocop will come protect us from bad guys, and they don't need explicit. Well, they actually want the explicit, or do you want the hybrid? Any opinions? Maybe Manolis?
Yeah, I think this will echo some of the opinions that were expressed in the previous question, it's the implicit and the explicit can cater to different things. So the explicit representations are very natural if you want to communicate with people, if you want it to be interpretable to people. So in some sense, there is a need to have some kind of explicit representation that is understandable by people, that people can actually parse, and that they can use to give some instruction or understand what action is being performed. If in any way a person is going to be interacting with the system, it will make sense to have some sort of structured explicit representation with which to communicate with a person. That being said, sometimes these explicit representations, the abstractions that they make, the choices for those abstractions may not be desirable from the learning perspective. So I think an example that came up is this, it's the metric maps, right? You have this metrically accurate map of an interior or an exterior. It's a very natural abstraction. People understand it. But from the learning perspective, maybe it's not always important to have metrically accurate reconstructions of everything, right? Maybe it's fine to have it, localized, have some metrically accurate geometry, but then between, places, you don't need to know exactly how far apart these places are. And in fact, this is also, how people think, right? That they don't have a completely accurate metric map of the entire world in their head. So I think these two sides of the coin need to coexist. There needs to be some kind of explicit representation that is interpretable to people, through which systems can communicate with people. But at the same time, we need to be able to back out of that and then do some learning, something that's a little bit more implicit, that is not subject to the constraints imposed by the particular abstraction that an explicit representation has, kind of imposed on us.
Yeah, thank you, Manolis. So for that one, for computer to build, learn to build a map, implicit sounds better. Backpropagation, latent space. For us, it's better to do on the explicit side, the human do something to fix. So we have two kind of database. Say Google Maps explicit, I believe. Then say for autonomous agents, maybe for Waymo, they have to have an implicit map of the world. They have to get two things in sync. So how do you actually handle? Do you build implicit by learning? Then somehow human use that to do explicit, or maybe they do independently. They don't actually talk to each other. Human just keep on doing explicit mapping for mapping human-facing applications. Then drones, autonomous cars, they just keep building implicit map for those applications. Or should we actually mix information?
I would be highly surprised if Waymo didn't have very explicit maps of every square centimeter of where they drive with their vehicle.
Yes, maybe Marc, from the Microsoft side, the applications, HoloLens. So it feels like it's very important to be explicit for debugging. So as long as things don't become fully autonomous, you have to debug. Or robots are part of our community. Not robots just work themselves. They have to talk to us, live together. So my feeling, explicit is very important because robots are part of our human society. I wonder if you see or share something from your experience, both from the professor as well as the Microsoft position.
And we obtained that from essentially doing, in very simple things. It's TSDF. So we use an implicit. Oops, can you hear me still?
Yes.
Okay. So it's an implicit representation where you do all the fusion, and then you'll extract a mesh through marching cubes like everyone. So that's what's happening. I think robots still have, the localization of robots and so on is still the precise localization. Self-driving cars, they use HD maps, and these HD maps are very, very explicit also. Now you can add to that other layers of other representations, but I think at this point, both robotics, mixed reality, all of those real applications, I don't know of much implicit learned kind of representations being used in any of it.
Yes, Niloy.
I want to say something because I've seen this confusion many times in original geometry processing or geometry community. Implicit has two forms of function. One is something like occupancy function, where it's a 0, 1. And then at anywhere away from the surface, I know if I'm inside or outside, no extra information. So it's very similar to explicit. But when we use sign distance field, it's a very specific type and specialized function. It has to satisfy the diagonal equation. And the beauty of this property of this representation is wherever I have a much higher amount of information because I know where the gradient is and which direction I have to go to reach the surface the fastest. If we are comparing this form of implicit versus explicit, I think implicit will just win, just because it has, at any point away from the surface, much more information. But if we are talking about implicit as in occupancy function, then maybe the difference is not that much. But implicit as a sign distance field or even absolute distance field, it just carries a lot more information. So it's not, you can go from one to another so easily. And I think that's a distinction that's worth remembering, and it comes up across applications.
Yeah, thank you, Niloy. And also, feel free to leave at any time. You have another appointment. Any other else want to chime in? Just Amir?
Yeah, so I think a number of points. So I think this discussion of implicit, explicit, I think in different ways it came up in the discussion too, whether it should be interpretable or not. I think that's directly related. So I think generally, let's say there are two classes of applications that people are working on. So in one case, you exactly know what you want. Like autonomous driving, I think more or less is one of those things that you more or less know what you want. Like there are certain behaviors they're trying to reproduce. There's a turn. This turn subject to certain rules, you know, your right turn, you have to stop for traffic, blah, blah, blah. Of course, not everything is like very well like followed, but I think it's something along those lines. And then the other set of applications, you're trying to get something to emerge at the behavior level, like a robot, you want to just task it with something, and this robot has to just finish the downstream task without, you don't really care how the robot sees the world, whether it sees something like through, you know, what form of 3D, does it have explicit metric maps or not? So you care at the behavior level, if you want to use like a psychology language, or like behaviors, they look into a box that is very complicated. They cannot look into it at the level of interpreting just the output of it based on the stimuli. So I think these two actually are important. I think that has been the biggest determiner of what kind of representations that you use. If you want to, like it came up, if you want the system to interact with humans, in some level it has to be explicit, because explicit and interpretability actually usually go hand in together. Like what do we call explicit? I think something that is interpretable for us as humans, right? What's the difference between them? And then I don't know, like VR, like Marc and the example that like Marc, you know, in HoloLens they're working on. I assume like, yes, that's true. So yeah, so I think it depends on what level you want your system to interact with the humans. At the behavior level, like you want your robot to just successfully clean the floor and you don't care about anything else, or there's something that you want to directly work on. You want to reconstruct the HD map of the environment because there's some sort of game that you're going to play in there, or there's some sort of augmented reality, virtual reality application that you're going to do. But I was going to say that generally this question, I guess it came up in the context of holistic modeling. I think if you look at the machinery that we have, I think we're generally behind in terms of solving the complex holistic modeling of 3D, regardless of what kind of representations that you pick. Like the system that we have, you're good at like low-level 3D, estimating depth, estimating surface normals, like so answering some of those questions. But if you ask a question that involves something at the general like layout of a room where objects and layouts interact, yeah, things are a lot more behind compared to that. So I think before you know, drowning ourselves in the question of like how it should be explicitly represented, we should acknowledge that we don't have as much progress on that front. And then once we are there, maybe just like, you know, the implicit explicit discussion that has been coming up for, you know, low-level 3D, we probably get to that. So in the importance of like being able to holistically model 3D, and whatever holistic means, I think everyone has like a different interpretation of it. I think that is probably more critical.
Yeah, thank you, Amir. I also agree that the more specific tasks, explicit makes sense, easier, and spot on. We are very far away from the general purpose robots, autonomous agents. So maybe still many, many years ahead until fully implicit has an impact. So for some years ahead, explicit, at least for the production side. Yes, I guess great for this question. And maybe Zihan, you can pick the next question to ask.
Okay, so let me ask the next question. And this is related to unsupervised learning and self-supervised learning. So compared to like, so nowadays we have a lot of 3D data sets, but compared to those data sets with like point clouds and meshes, it seems like it's more challenging to get data sets with structured annotations. They're still very scarce and hard to obtain. So how can we, is there any thoughts about how can we leverage unsupervised learning or self-supervised learning to help learn the holistic 3D models?
Well, we have good sensors for 3D too, unlike semantics. So they, like, there's no sensor per se for like take an image and give you boundaries of objects or classes, whereas for 3D we have that. So maybe part of the reason that we actually think about even higher level like holistic 3D is the fact that we have sensors for lower level ones. I don't actually believe completely in actually using sensors for like replacing them with RGB cameras, because I think there should be a source of like supervision to be able to solve same problems without those expensive 3D sensors, but using RGB cameras ultimately. But in terms of then pushing the boundary, going from like low level to high level, I think, again, this might be biased a little bit based on things that I have been working on, but I believe in this case in relying on emergence of some of these properties based on, you know, a downstream behavior rather than, again, explicitly demanding a certain 3D property to emerge as an unsupervised, through an unsupervised learning process. So let's say, like when we're working on navigation, like training agents to navigate in indoors spaces without, based on like reinforcement learning. So you would just train a reinforcement and policy to act like a controller to receive like a stream of visual data after going through some abstractions and get them to navigate, do point navigation. So layout, for instance, emerge in the internal representations of these agents, which makes a lot of sense. If you give your agent something like depth and you task it to learn how to go from point A to point B in a building, you would think of it as like it has to build some sort of layout, course layout of the building. I think Saurabh Gupta had this paper on cognitive mapping and planning. So cognitive maps are actually a good testification to that too, is that there's some sort of map that gets reconstructed through the virtue of wanting to navigate. So I think in that sense, that's a signal for unsupervised learning because nobody built in these explicit maps or nobody directly supervised them, but they emerge as a result of being demanded. So being able to ultimately link the 3D or low-level 3D representations that we have to some higher level downstream behaviors, whether that could be like navigation or manipulating an object. Imagine if you want to manipulate an object, but all you have is some sort of pixel-wise 3D about it. You would think that you have to create some sort of a CAD model looking like, implicitly, CAD model looking representation of this object through your weights, whatever that is in your system. It's a neural network or anything. You have to be able to model piecewise modular model of that to be able to, you know, reason that, oh, this part moves, this is an arm, this part doesn't move, this is rigid. So emergence by connecting low-level representations to downstream behaviors, that would be one guiding signal.
Yeah, I agree. I mean, seems like if you can somehow enforce the system to learn something, like, you know, come up with some task that you have to use some of this kind of holistic reasoning to be able to accomplish. That's probably a very nice way to achieve that without even supervise it in a holistic way. Any other suggestions or thoughts on this problem?
So I think Amir's answer focused a bit on saying that some of these properties will emerge naturally if we look at interesting tasks. But there's also an alternate way, which is, let's say we have an explicit representation in mind, or some concrete representation in mind, which we want to predict. Maybe object bound, it having notions of separate 3D objects is one good idea. And even there, we can leverage some unsupervised, self-supervised, whatever techniques, because having this concrete representation does impose certain constraints on how we expect the world to emerge in future. So for example, if my prediction system inferred some representation and I'm watching the video and I saw different components moved that were, different from what was possible given my prediction, then that's sort of a signal that my grouping prediction was off. So even if you have a concrete representation that you want and don't necessarily want something to emerge, you can still verify whether your predictions are consistent with how the world is changing, or what the effect of someone interacting was. And maybe that's a useful signal.
Yeah, so I just want to add, I'm completely believe that it is possible to bridge the unsupervised to supervised. If we really know what kind of structure supervision is trying to guide the system to learn, right? The measure of the order or structure, the supervision, or let's say straight lines or symmetries, patterns in code, help simplify things, help summarize things. Right now, so if we know the principle behind it, how do we measure, right? I think the goal for learning for supervised and unsupervised should be uniform. They're trying to optimize certain things, right? Let's say simplicity, model. And if we know that, the boundary between supervision and unsupervision may become blurry. For example, I can supervise, say there's a line in the image. Oh, that's 2 parameters. But if there is a way we can measure, enforce when our neural networks or our learning lesson eventually rules down, oh, I only need 2 neurons to interpret the data. I don't even need to know what the 2 numbers are, but I know that's, have reached the same kind of simplicity or compactness as explicit supervision. So this is something I think currently there's still a gap, but I think we're getting close, right? With the understanding of the gap between supervision and unsupervised, self-supervised is getting close. And I firmly believe there will be a unified, purpose or measure of simplicity or learning that doesn't really matter that you provided the machine with some supervised or semi-supervised information, but or even without that, if the data has such structures, and the machine should be able to find it, right? So this is my personal. So also to indirectly answer the question, right? I think for the question that yes, holisticity, the label data is always short, right? We have to have a human to label it. We don't have sensors for it. So that actually makes unsupervised or self-supervised learning even more important for this. How can the system find the mechanism behind it that guide the system to learn, to simplify, to do the abstraction from the data, unlabeled data. So I think that's a very, very exciting and also, challenging task for the future.
Yeah, totally agree. Florent?
Yeah, so maybe it's not a response, but more remark regarding the question is on the production of the data sets. We all know what is a point cloud and a triangulated mesh. And if you want to produce data set based on that, okay, we know what is expected output, and we know how to fit the data set. But if you talk about, I would say, general CAN models, the formalism is very not well defined. you have plenty of, in terms of 3D models, you have plenty of possible models that can be different. For instance, you can have CAD models that only have the exterior envelope of the object. In some part, you will have interior facet. In some cases, interior facet will self-intersect. In some cases, interior facet will be just random. In other words, they will correspond to some part, structural part of the object. So it's not well defined at all. And yeah, one of the challenge today, I think it's to create generic data set of CAD models by kind of agreeing on the formalism of this model. You cannot take randomly CAD models online, 3D CAD model, and put them in the system, because you will have some problem with the meshing operation and things like that. It was just a remark on that.
Thank you, Florent. So in the interest of time, I'm going to pass my the opportunity to Yasu for probably the last question for our panel discussion.
Yes, I also to mention Marc had appointments, had to leave. It's getting late in Europe. So let's make this last question in short. In 5 years, in what problem in your area of interest you are still hopeless in solving? So 3 or 4 years ago, I asked a very notable computer vision researcher, top researcher, deep learning is really coming. And do you really believe that deep learning can solve anything? The answer was yes. Maybe surprising if you're here right now, but back then, it's really, we are solving every single problem. So given enough data, we can solve. Maybe true, give enough data, but we begin to realize not enough data. So many problems seem still impossible to solve. And for my case, I've been working on this holistic or CAD-like reconstruction from raw sensor data from the start. It's difficult. State of the art is a hybrid. Optimization, classical plus deep learning. Never deep learning just end to end. So to me, there are many problems which are just hopeless in tackle in 5 years. So I'm curious to hear for what kind of problems you think in 5 years still we cannot solve at all. Could it be autonomous car? We are still far from. We can say that. So curious to hear for the kind of problem you are interested in. In 5 years, we probably cannot still solve at all. What are such problems?
Can you tell us who the prominent computer vision researchers that said you can solve everything were?
Maybe later offline, because that's maybe wrong prediction. So I will share offline later.
Yeah, that's accountability.
Does anybody want to share maybe this problem? I feel hopeless in solving in 5 years.
So that kind of claim has been made repeated. People, history repeats, right? I think human never learn. That's the problem, right? Maybe deep networks learns, but we never from the errors. But human, we never learn from our own errors. That's actually, unfortunately, even make us doubt we are truly a neural network, right? So, so that's the comment.
That's why we need to know who they are to not listen to them again.
Yeah. So I think we are better. I mean, individually, right? People say things for different reasons, publicly or privately. I think individually, I think we all very much know where we are in terms of, at least for our own field, right? Our own, just like Yasu is. Knows what's really best for holistic for this raw data to CAD-like model. Similarly, I have my similar experience as well, and so by the end of the day, right? So deep learning or other tools, PCA or multi-view geometry, epipolar geometry, they're just components, guys, right? They solve the problem, and sometimes, but of course, just like Yasu said earlier, there's at some point of the history, people always try to overblow something that make a bubble, right? And maybe that is important. It's new at the time. and people don't have certain things we don't know. When I started revision, I know nothing about epipolar geometry. It was really, really fascinating to sort out the math, multi-view geometry, right? As the same, captivating as a deep learning probably these days, because there are mystery, there are things we don't know about it. But after that, you realize, and we can be much better. We realize what really it is and what it's capable of, and we move on and we get to the next challenge. That's sort of comments on this. Yeah.
No, and also I would have to add. Oh, sorry. Yeah, go ahead.
Yeah, so just for the defense of this notable researcher, the statement was given enough data, we can solve anything by deep learning. So getting data is very hard. So just for the defense.
Yeah, sure. No, I was actually going to say that, like, jokes aside, no, I think clearly, like, there was something useful, say 5 years ago, that we have now and we didn't have then. So of course we got something out of it, and I think it was useful. It would be foolish not to use it or not invest on it. And nobody really knew, and even now knows, the extent of how much, like how far this would go. So I think as a researcher, like, clearly we don't need to completely see the future. Like, if we knew it exactly, it wouldn't be called research. It wouldn't called exploration. Like, it being wrong once in a while is part of the game, but we need to make the step in the right direction. So, it was, jokes aside, I think it was a good direction to take. I'm personally very happy with it. Like, at that time I was a graduate student, and deep learning happened in the middle of my PhD, and it changed completely my happiness in life, regardless of my research. Is like, before that, it was all like, if you look at the recognition, it was like all SIFT plus some SVM, and then it would be sort of pretty hopeless to think of that, yeah, AI is going to emerge as a result of a combination of SIFT and SVM, or maybe making it a little bit more hierarchical, a little bit, playing around in that space. So now I think we're talking about the same thing in 3D. Just to now give a more serious answer to the question. I mean, I would say one thing that is interesting, I think, is that our exploration so far in the context of 3D has been driven by more curiosity rather than demand by downstream users. Let's say if object detection is something that there's various demands for it, like industries demand for it, and I don't know, it's a very sensible task. In terms of 3D, if much of the things that we have done, of course, there's a lot of demand for 3D too. But let's say a question that I think it might be obvious to us here, but maybe not to everyone, is that, like, why do you even need to go holistic or more holistic in terms of 3D? Like, what are we trying to get out of it? So in that sense, I think many of the properties that we want out of our 3D vision systems might not be obvious right now. So Shubham mentioned it earlier. I think it's really important to have predictable, like actionable, predictable, like action conditions, some sort of representation, some sort of reasoning about the world that is integrated. It has semantics and 3D integrated. It's predictable, and it's predictability in terms of condition on my actions and not condition my actions, some sort of autonomous states of the world. Is that if I drop an apple, it's going to come, like, go down in this particular direction, and if I intervene by some of my actions, then it would happen this and that. So kind of like what in robotics people want, like, through their dynamics model, to inform the behaviors of their actions based on what they know now, but towards the future, towards like solving some downstream goals. So I think in, let's say you asked like 5 years from now, that would be the time span. I would be interested, well, I think realization of the importance of these properties depends on probably what we want to do with these systems. I think robotics is an application, the most, I think, obvious application that comes to mind. I would be curious to hear others' opinion that would guide our exploration in this direction. Maybe AR, VR too. So, so I would say in 5 years we would not have solved the problems that robotics and AR, VR in 5 years would be demanding us.
Yeah, thank you very much for the very good thoughts. Shubham, then the Manolis after that.
So I just want to support what Amir said and make it slightly more concrete in my opinion, as in, so especially looking at robotics, they use a lot of these sensors, which are very different from the kind of sensors that humans have, or explicitly hard-code world models or models of the objects that are being interacted with. And for me, really, the goal of a lot of research that we do in perception is to be able to replace those with perception systems that, here's a robot that has similar sensors to what a human would have and no additional extra knowledge, and yet it can perform all these complex tasks. And that's maybe sort of the goal for me for all the holistic and physical representations that we are trying to predict. And I do think that 5 years is a bit too soon for that to be a realization. Like if you attend RSS in 5 years' time, they'll still be using these sort of sensors or additional world models in more than 80% of the papers. But hopefully that will change in the long term.
Thank you. Manolis?
Yeah, I think my perspective will echo some of what both Shubham and Amir said as well. And it's kind of the observation that, we've been talking about, holistic 3D, this is the research area, the problem space. But a lot of these concerns, applications in robotics, AR, VR, these kinds of downstream concerns, it's not just 3D, it's 4D, there's space-time, right? There's, for things to be actionable, for things to be predictable in some sense, there needs to be a temporal axis. It must be an evolving structure. It's not statically frozen in time. And I think we will probably need to pay quite a bit more attention to this, the temporal axis, look into, dynamic reconstruction, look into acquiring properties of the real world that are important for the temporal axis, like physical properties, the masses of things, coefficients of friction, things like that, which, are important when you start to think of time and, physics. So that I think will remain quite challenging for the foreseeable future. It's going to be, it will not be solved within the next 5 years, probably not even 10.
Yes, Florent.
Yeah, it's so I agree that there's something important to do with holistic 3D for robotics, but I think the potential market that holistic 3D can address in the coming years is really huge. Potentially, I think the market is here, except that today, from my point of view, what we produce in computer vision and computer graphics in terms of holistic 3D models is not at the level of what is produced interactively by designer or operators that will create models of cities, for instance, or do reconstruct some mechanical pieces for reverse engineering, or designs objects or things like that. We cannot do automatically what they are actually doing, and right now we're not competitive with them. And but I think the market to address is really huge, and when we'll make progress, actually, I think it will open a lot of perspective for application, not just robotics. It's my point of view.
Yeah, thank you. So I guess maybe it's about time to wrap up. Typically for 5 years, we tend to be pessimistic. Oh, there are so many problems we can solve, but on the positive side, we have lots of great problems to tackle as a research community. Dr. E?
Yeah, I'll just have a quick, comment, right? So, I think it's Bill Gates said, right? So you always overestimate what you can achieve in 1 year, underestimate what you may be able to achieve in 5 or 10 years, right? Every single time he made a prediction, he has been wrong, right? You set a goal for your 1 year, usually but in 5 years, 10 years, a lot of things could happen, with effort. So, my best assessment is that for any with the resource, especially the current practice, right? We can throw 1.3 trillion parameter at something, and with the per iteration cost $1 million, right? You can make a lot of instance to happen. Okay, we will have a lots of remarkable, right? We can have a system can beat people at the AlphaGo, right? At Go, or maybe memorize the text in the entire data, internet. That's fine. I mean, people can get marveled at that. It's marvelous. But the point is that I think there's one thing will be happy we make even progress in 5 years is that our capability to, what are the mechanisms that we are capable to learn new tasks in the new environment, right? Taking the past experience or knowledge we have, even models we have in certain areas of our world, or the sensors we have, doesn't matter if it's human sensors or, and we try to learn new tasks, new actions, or new. So, and also at a very minimal cost and risk, by the way, right? So for example, gymnastic can learn how to take a tumble on the balance beam before kill herself, or right? So you have to, she has never done this before. So what is that process? Allows human, or diving from a 10-meter platform without killing yourself, right? So having even equipped that ability to the machines, robots, right? So there's one comments, right? I had a conversation with Harry Shah, former vice president of Microsoft. He said that, even we have reinforcement learning can do a lot of remarkable things, but it really relies on one thing. They have to all learn in a safe environment, which means that all the example you saw today is in simulation. In the environment, you have a simulation, right? But once you take those systems out of the real world, the risk cost is way too high. You cannot do, you just cannot afford this kind of iteration or learn from error. It's something wrong with the methodology, basically. I'm not saying entirely wrong, it's useful, but basically that's not the same principles our human living beings utilize. Or we should transfer that to robots, real world robots. That's what I'm trying to say, right? So the way integrating information, past knowledge, the current information, and help with learning a new ability, exploration in a safe, economic way, right? Progressive way. And I think that's something, I would like to see we even make some good progress in there. Right, but other specific tasks, fine. If you have enough data, enough computation, you only care about one instance. You don't care about the methodology is transferable. I think in 5 years, we'll have a lot of examples like that.
Yeah, thank you. Yeah. Yes, indeed, it's important to understand our amazing capability to adapt to our different scenarios or handle rare cases in which computer vision seems to be lacking.
With a hard bound on the economy and also on the safety, right? So you learn in a safe and economic way, right? Rather than, make every project Apollo project. Well, fine. I mean, it's great achievement, but that's not going to help me or help, help average living beings, right? So this is we have to make that distinction, right? This is really the different practice of methodologies, right? We should not always hang on the one. I mean, there's so many, capture people's current imagination. There's a much bigger price, to go after.
But I would like to add one point on top of what he said. This is more on the lower level side. So in terms of wanting to work on methods that can seamlessly generalize to new tasks, I think prior to that, I think that's definitely a desire that we all have. I think prior to task generalization, I think we need to work on the problem of adaptability. So we have systems that right now can solve, let's say, one task in one environment. Before wanting them to solve multiple tasks in all environments, let's just get them to solve that one task everywhere robustly. So I think that's an easier problem that we have underestimated. I think adversarial attacks was just a sort of a manifestation of that issue, is that if you add a little bit of like imperceptible perturbations to some images, all of a sudden the output completely changes. The fact that you can do it regardless of, you know, the practical ramifications of it. So I think getting the system that we have, like the things that you can do in one building, in one environment, on one data set, just reproduce that capability everywhere. Being able to provide that as a guarantee is something that we are far from. And so then that is exciting in a way, actually, to me, because it's exposing how much we don't know about the things that we are working on and how far they are probably in terms of the mechanisms that they use for solving the problem from something like, you know, humans or biological organisms that can somehow solve the same problems very robustly. So I think in that sense, my guiding star is not something like a Apollo or let's say human, like Holy Grail is not like human perception to me. Something like a rat that can safely navigate within its, you know, 10-meter radius safely, but everywhere.
Thank you.
We don't even know how birds migrate in miles, right? Thousands of miles, or turtles, right? I mean, so I think at a very, very low cost, guys, you know, minimum, small, tiny brain, very lousy sensors, right? I mean, you know, low energy, highly, you know, secure, right? They never, you know, fine, you know. So this is something I think fascinating. There's some basically fundamental laws and rules we are really missing with the current practice. That's nothing wrong, and they're useful, right? I mean, fine, you can have. But the kind of practice, even the success, right? So AlphaGo, now they fight, the dog fight, you know, DARPA, fine, that's a simulation. Humans are not very good, right? Then also it's a safe environment to train the simulator, right? The AI machine. Because you can simulate that knows everything about there. You can fail billions of times before you could crash millions of aircrafts before you learn one maneuver, right, can beat human. But in real world, you don't have that, right? Well, nature paid that price through natural selection, but we don't want to, you know, spend the same amount of resource and time to repeat the same mistakes we learned, right? So the question is, how do we do this in a much better way? I think that's fascinating. A lot of has to do with vision, right? This is the most challenging task our brain embark on. We have learned a lot of new mechanism to do this in a effortlessly, in a very, very economic, very, very effortless way. So that's something that I'm just fascinated, you know, that's something I'm, you know, really like to know more. I mean, in 5 years, not myself, but, you know, collectively as a community, we can make some progress. That'll be fascinating. Yeah.
Yeah, thank you. This could lead to another heated 2-hour discussions on synthetic versus real. You know what that means. Let's wrap up. I'd like to thank all the panelists for joining the discussion in this, for some late hours, some early hours, and also participants for joining across the globe. For just a last note, this was recorded, so if you want to watch second time, third time, you can. Maybe for others, your colleagues, you can pass to the others. There's an interesting discussion. Hopefully there was many interesting, insightful discussion for people to watch and share. Thank you very much again for all, and have a nice day.
Yeah,
Bye.
Thank you very much for organizing this, Yasu. And
Thanks for organizing and moderating.
thank you, everyone. Hi, guys. Bye.
Thank you very much.
Bye.
Bye-bye.
Thank you. Bye.
So I stop recording now.